In the last few episodes, we were busy building up a program counter circuit, which allows us to run through the instruction addresses in a program. As a concrete example, we were looking at this imaginary program, and we used it to come up with ideas how the program counter has to be able to jump from instruction to instruction. As a next step, we actually need to be able to store this program somewhere. To do so, we are going to add a program memory to our CPU, which contains the instructions that we want to execute. Be sure to like and subscribe if you want to see this project unfold. So for this memory, we're going to use a fresh new breadboard where we can build up the surrounding circuitry and also have some LEDs to look at what's going on and what's coming out of the memory. As usual, let me start by connecting the power rails of the board. And also add some decoupling capacitors. Now, as a memory, we are going to use one of these SSD39SF memories. These are flash chips. They're pretty useful because they are fairly big. The smallest one is 1 megabit, and they go all the way up to 4 megabits of storage. And they have a whole bunch of input addresses, and they produce an 8-bit output signal. So basically, whatever address we present at the input of the flash is going to produce the value that is stored at that location. And in this way, we can use the flash basically as a program memory, where the program counter will present the address of the current instruction to the flash, and the flash will respond with the current instruction for the CPU to execute. So let's place this somewhere where we have easy access to the pins. And as the data comes out of the flash memory, we want to be able to look at it and see what the memory is currently producing. So we're going to use one of these bar graph LEDs that we've used before. Let's bring this all the way over here for simplicity's sake. And let me add a resistor array. Tie that to ground. As usual, let me do a quick check if the LEDs are working properly. Perfect, that seems to be working. As a first step, let me hook up power and ground of the flash chip. Next, let's hook up the chip enable line and the output enable line to ground. These are active low signals, so this will permanently enable the chip and also permanently enable the outputs. So it will actually produce whatever the memory location holds at its output. Pin 22 is the chip enable. Let's tie that low. And pin 24 is the output enable, which we're going to pull low as well. Now, these flash chips actually allow you to also modify the data that is currently stored inside, but we're not going to use this at the beginning for our program memory. So the write enable line, which is up here in the corner, we can tie high, which disables the write mode and just constantly puts this into read mode, such that the flash basically acts like a read-only memory. Now, these flash memories can get quite big. This one, for example, here has 1 megabits of storage, but the largest one available in the same packaging has 4 megabits. So there are a lot of address lines up to address 18 that allow you to select from those 4 megabits. But our current program counter is only 8 bits, so let me actually tie all the addresses to ground except for the lower 8 bits, which are going to come from the program counter. This will basically allow us to just address the lower 256 bytes inside this flash, which is going to be enough for the beginning. So let's start at the right-hand side of the chip. So from the top, the first address line is address 17, which we're not going to use. Address 14 we won't use either. Address 13, address 8, address 9, address 11, and address 10 here in between the control lines. They are all going to be tied to ground. Now on the right side, the remaining pins here are actually the data outputs, so we'll leave these open for now and move to the left-hand side of the chip. From the left, the first pin is address 18, which we're going to tie low. Next up is address 16, address 15, address 12, and then the next 8 lines are address line 7 down to 0, which are the ones we're actually going to use. And then following that are the first 3 data outputs, with the next 5 being on the other side. So it might be a good idea at this point to actually hook up the data outputs to the LED bar graph over here, so we can actually look at what's coming out of the memory. Okay, bit 0 of the data, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7, perfect. Now for the first tests, let's hook up the 8 address inputs of the flash to either ground or 5 volts through a jumper wire. So we can actually choose an address and see what's inside the flash. So address 0, address 1, address 2, address 3, address 4, address 5, address 6, address 7. So currently all the address inputs are tied low, so the flash should produce whatever is in at address 0 on these LEDs over here. So let's give this a try. And that seems to be working. We get a output over here. Now usually from the factory, these flash chips, they are pre-programmed in a sense to all ones, but I programmed a random sequence of data in here just to give it a test. So if we change the address bit 0 and jump to address 1, we see a different pattern showing up over here. Now let's take a look inside the flash chip itself and see if what we're seeing over here on the LEDs is actually what we expect and what is actually programmed inside of the flash chip. And then let's see if we can figure out how to program a more interesting pattern into the flash chip over here. So we get something over here that is nicer to look at and easier to recognize. So let's remove this flash chip here. And let's insert it to this handy little programmer, which can be used to program all kinds of memory chips, but also test logic chips and work with small-scale FPGAs. So this is a pretty handy and cheap thing to have. So let me put this flash chip in here. And now let's see what's actually on this chip. I'm going to use a handy little program called MiniPro, which can interface with this programmer that I have plugged the flash chip into. So MiniPro -P to indicate which chip we're using. It's an SST39SF, and it's the 010 variant, which is the 1 megabit one. And we want to read what's on the chip and store it in a file. There we go. Let's take a look what's in there. So what we've just read is the binary data that is inside the chip. So let's use XXD to work with the hexadecimal data. Work on single bytes, 8 columns to make it easier to read. And let's read in this rom.bin that we've loaded from the chip and store it in rom.hex. Let's take a look inside. So this is now essentially the contents of the chip. And as you can see, it's the entire 1 megabit of contents. But we've been looking at these first few bytes by toggling the address lines manually on the breadboard. So C5. If we convert hex C5 to binary, we get 11 followed by 3 zeros, 101, which, if you recall, was exactly what we were seeing on the LED bar graph. And also the next byte seems to match what we've seen on the bar graph. Now let's come up with an interesting pattern that is easy to recognize, and let's try to write that back into this flash memory. So we have 8 LEDs. And basically, we want to light up each LED from right to left. So this is the pattern that we want to program into our flash chip to get this pattern where we light up each LED in turn from right to left. So let's actually do that. So first up, we light up the first LED, that's a 01. Then the next one, the second LED, that's the hex 02. 04 for the third one, 08, 10, 20, 40, and 80. And then afterwards, we might want to actually go backwards again. 80, 40, 20, 10, 8, 4, 2, which should basically be the pattern backwards again. So let's save that. And let's see if we can get this to work. Let's use XXD again, but in reverse mode to go from this hex representation back to binary. Okay, so let's program this modified binary back into the flash and see if this works in hardware. So we use Mini Pro again, but this time with the -W option, which is going to write the binary back. That seems to have worked. So let's put this flash chip back into our breadboard and see if we can look at the pattern that we just programmed. Let's power it up. This looks already very promising. So currently this is address 0, and indeed this is the hex 01 that we programmed. So if we step to address number 1, we should actually see the next LED light up. Indeed, that's the case. Address 2, as expected. And address 3 has the LEDs basically turning on in sequence, which is exactly what we expected. Now, instead of toggling these wires manually, let's actually hook this up to the program counter we've been building up in the previous videos. And let's see if we can use the program counter to step through the addresses, which should give us a nice moving pattern over here. So let's take the program counter output, which is right here, and bring that down over here to the addresses. All right, let's power this whole thing up. First of all, we need to connect the power connections of this new breadboard here. That should do the trick. So let's power the whole thing up. And that looks quite promising. The program counter is currently pointing at address 0. And correspondingly, we see the contents of address 0, which was the hex 01 we programmed into the flash, appear down here. So now if we step the program counter through individual byte addresses, we should actually see the different memory locations be read out here, which with the pattern we programmed should basically be this LED just wandering over and back again. So let's see if that works. First take it out of reset. Address 1 is hex 02, hex 04, hex 08. Then address 4 is hex 10, hex 20, hex 40, hex 80. And then address number 8, the next one, is going to be the same again. It's hex 080, and then 40, 20, 10, 8, 4, 2, 1. And when we move even further, we go back to basically the remainder of the flash memory, which still has the random data in there. So can just let this run. And basically you see the individual memory addresses be read out. And if we reset, we should see the pattern again that we were programming into it. In the next episode, we will try to come up with the first basic instruction encoding by connecting the bits that come out of the program memory to the control signals of the program counter. Thanks a lot for watching. Like and subscribe if you'd like to see more of this, and see you next time.